Two safety standards that we'll look at is OSHA, uh, Occupational Safety and Health Administration, right? And then their 910 standard, and then the National Fire Protection Association 70E standard. These are both safety standard, electrical safety standards. Topics we'll be looking at, of course, is electrical hazards and energy. We'll look at the 910. Now, the 910 standard, you can come get this if you want to look at it. This is the industrial regulations. So this is the OSHA 910. You can take it back. Of course, this covers all kind of stuff, but subpart S is the one that covers electrical safety. Okay. And then the 70E requirements. We'll talk about what qualified worker is, electrical safety, work practices, understanding arc flash hazards and categories, personal protection equipment, and approach boundaries, and implementing 70E and 70 qualifying employees. Okay? Okay. So this was the earliest thing I could find was between 2003 and 2010 when I went to the Electrical Safety Foundation International. This is where this information came from. 1,738 electrically related workplace fatalities, 13,150 severe injuries. 80% of all electric energies are caused by what we call arc flash. And we'll talk a little bit about more of that. Cardiac arrest and respiratory failures is one of the major causes of deaths in electricity. Muscle, nerves, and tissue destruction when current flows through the resistance of the body. You know, when high current flows through resistance, it creates heat, so it'll literally burn you from the inside out. Burns, of course, from arc flashes. Thermal burns too from arc blasts or arc flashes. And then secondary injuries. Secondary injuries would be like you get hit by an arc blast and you fall back and hit your head and stuff like that. Of course, I thought that was cute, right? Electrical shock. Electrical shock is received when current passes through the body. The severity of the shock depends on the path the current takes, the amount of current that flows through the body, and the length of time the body's in contact with the current. And just because it's low voltage doesn't necessarily mean it's low hazard, right? It's just that the lower the voltage is, the lower the hazard. The higher the voltage, the higher the hazard. So pretty much, well, most voltages will cause some problems. Body resistance is just a lot of this is not a fixed quantity. Your body resistance varies all the time, and you can measure it with your own meter. What depends, of course, is that depends on the path. You know, what path does it take through your body? These are just some examples: hand to hand, hand to foot, foot to foot, hand to hand, etc. It also depends on whether you're wet or dry. If you're wet or if you've been sweating a lot, sweat's real bad because it's salt water. Salt water has fairly low resistance. So if you sweat a lot, then the resistance of your body goes down a lot. Also, if you've got any open wounds, your skin is a pretty good insulator. But if you've got an open wound and you get into actually meat, then you have inside you have very low resistance. So the main part of your resistance is through your skin, yeah. Open wounds, AC and DC. When we get into AC, we'll talk about frequency too. So it depends on whether you get into AC, alternating current, or direct current. And of course, electrical current flow, touch potential. This would be one of the most, anything that takes you through your heart or your lungs are your most serious. If it goes to your heart, it could stop your heart. Your heart works off electrical impulses, right? You understand that. And if you interfere with those electrical impulses, then your heart could go through fibrillation or get out of sync. Fibrillation means your heart is out of sync, which means the beating of your heart and the opening and closing of your valves are not in sync with each other. And if your beating of your heart and your valves get out of sync, then your heart's not going to generate any pressure. It's not going to pump, even though it's beating. So it's beating erratically is what it is. These paths are really dangerous paths. Hand to hand, of course, foot to foot, which will take it through your lungs. Left hand to left foot, or right hand to right foot. I've got that backwards. This would be right hand. Okay, we okay? These are some of the most serious paths you can get into. This was a pretty interesting slide that I found on the internet that basically gives you the resistance between different places. Ear to ear is probably the lowest current path through your body. So I was watching a movie today with Kevin Costner, Killed in 3 Days or something like that, and he was putting a car battery between the guy's ears, and that would be, even though you're dealing with 12 volts. So read your, yeah. Current dry skin has a pretty good deal of resistance, and this is relative to 110 volts. We call it 120 volts over here. So if you got into 120 volts between your ear to ear, that's going to be about 1.11 amp, and that's going to fry your brain. If you get into dry skin, though, if you get into 110 volts with dry skin, that's 1.1 milliamp. That's not even the threshold of pain. Right around that, you can get a little bit of shock. Hand to hand, 500 ohms. Pretty much you're above the threshold. Now, 50 milliamps is considered to be the potential of being a lethal current flow. So this could be very dangerous right here, hand to foot. In wet skin, 110 volts wet skin, and it doesn't say which direction it's at, but these are just some examples of the different resistance that we have in different locations. So not only does your body vary with resistance, you have different resistance depending on where you get into a circuit at, right? Does that make sense? These are electrical shock effects. And notice what was interesting to me is that women have a lower threshold of shock than men. So it says if we get into if we get women can slight sensation at 600 microamps, where men have a slight sensation of around 1 milliamp. Which I thought this was really interesting. This is AC. Now notice AC, you feel it even at a lower voltage. You feel it at 40 milliamp, 400 microamps, where a female was feared at about 300 microamps. And then at 10 kilohertz, then the current. So the higher the frequency, the less effect you would have. So here it would take like 7 milliamps for you to feel it. This is and you won't even feel it. Here's where you actually get into the threshold of bodily perception. So 5.2 milliamps, women 3.5, right? Depending on frequency and also DC. Pain and voluntary muscle control maintained. So what they're saying is if you get into this right here, then you might not be able to let go, because now the current is overriding the impulses to your brain. So it's going to cause your arms and everything, or hands, to contract, and it's real hard. Your brain is saying let go, but the current is overriding that. Here, pain of now here we're getting into lethal, right? You understand? So AC is a little more dangerous than DC. So here, 9 milliamps, you might lose control of your body with 9 milliamps at 60 hertz. Now, of course, 60 hertz is what is the frequency that we use here in the United States. You know, over in Europe, they use 50 hertz, but here, this chart is set up for 60 hertz. Then we get into 90 milliamps of DC, which would be about 23 milliamps of AC, 60 hertz AC, then difficulty breathing, and then you get into 500 milliamps of DC or 100 milliamps of AC, then your heart can go into fibrillation, which is not good. So this was very interesting, is that just the amount of current flow. Now, what determines the amount of current flow? What two things determines the amount of current flow? That's a question. Yeah, but what things determines the amount of current? Ohm's law says I is equal to what? Divided by R, right? So it's how much voltage you get into divided by the amount of voltage you get into, which is this guy right here. So the current is what? The amount of voltage you get into divided by the amount of resistance your body has between the two contact points. So here they don't tell you the amount of voltage because that's going to vary with the voltage and with resistance, right? That makes sense. The two electrical safety standards that we have is OSHA, the 910 standard, and then also the National Fire Protection Agency 70E standard, which covers electrical safety in the workplace. This is general industrial regulations. So the 70E is set up specifically for electrical safety. OSHA, that's the Occupational Safety and Health Association. This is one of your government bodies. This is one of your main government bodies, is OSHA. And you'll hear about OSHA a lot. So OSHA sets safety standards. OSHA is law. So if you break OSHA regulations, then you can really get into trouble. A 70E is a standard that has to be adopted, and this is what we'll look at in a second. So is it law? OSHA set 910, I just told you it was, right? The National Electrical Code, is that law? Is it law? Okay. National Electrical, NAFTA 70E, is that law? Okay, so you just made 30% on that quiz. So OSHA is law. NEC is law only if it's adopted by the local authority having jurisdiction. So it is not federal law, and it only becomes law if it's adopted by the local authority having, yeah. Right. And they adopt NEC. They adopt the National Electrical Code. Both Birmingham and Jefferson County adopt that. But if they don't adopt it, it means, or they don't go to the new standard. So they change the NEC every 5 years. So I think the last change was in 2015. So a new code book is going to come out in 2018. It's highly unlikely that they will adopt the 2018 code until they figure out everything that's changed about it. So it takes a little while, and they don't have to adopt it. And there are some cities that have their own code. So cities can develop their own electrical code. Yeah, well, so that's not electrical safety, though. That is just a safety code. And they can add to the National Electrical Code, or they can adopt sections of NEC, but they don't have to adopt it at all. So basically, NEC is recommendations. Now, the 70E is also, the 70E, if you're employed by the Department of Energy, it is law. But for no one else, OSHA has not adopted 70E. It says, however, 70E helps employers meet the performance requirement by OSHA 910. And of course, a lot of employers are very, very interested in safety, electrical safety. It's a big deal now. And that big old book, 70E, only covers the 1910 standard is subpart S. And we'll look at a little different here. So National Electrical Code, and a lot of people think the National Electrical Code, NEC, is safety. It's not safety for people. So what NEC, National Electrical Code, covers is the safe installation of electrical wiring and equipment. So it's how to install it safely, right? You'll understand. How to prevent things from burning up and how to prevent things from flying apart. Now, if you do that, your installation is going to be safe. And this is one of the things that the National Fire Protection Association realized, that there was no safety rules for preventing people from getting electrocuted and preventing people from getting hurt by arc blast. So that's when they came out with a 70E standard. So 70E covers electrical safety requirements for employees. So that's why they came out with a 70E standard. OSHA 910, of course, this is a link to OSHA 910. Hopefully it's going to work. We'll see. And so this is OSHA 910. And that's everything in this big old thick book right here. And what we're doing is we're interested in subpart S, which deals with what? HIJKL. So this guy covers material handling, helicopters, derricks, crawlers, but the whole part, subpart S, deals with what? Electrical safety. So this whole paragraph right there, everything. By the way, they leave a lot of room for expansion. So right now they have the .301, .302, 303, .304, .305, 306, 307, 308. And then it jumps all the way down to 331. And then 332, which covers training. 333 is workplace practice. And so it looks like it's real long, right? You see that, but most of these numbers are what? Are reserved. They're not used now. Let me I know it's hard for you to see. Of course, you can move up a little bit. So this is subsection S, which basically starts with 300, and it looks like it's very, very long. But notice all these numbers are not being used. So the only ones that's being used is wiring designs, protection, wiring methods and components, equipment installation, hazards, special systems. Then it jumps down to the 333, which is selection and use of work practices, use of equipment, standard for personal protection. Now this would probably be the best place to go, because this one that we have right here was actually published in 2014. Where on the one online would be what? It's going to be updated all the time. Okay, does that make sense? So we're just going to look at just basic parts of this. So safe installation is covered in 301 to 308. Then workplace practice, which I have highlighted in bold because we'll look at that in a minute. Then definitions is 399, and then it's got an appendix. So 3.1 applies to qualified and unqualified employees, and we'll look at what that is. Premise wiring, connection to supplies, other wirings, optical fiber cable, and then this section right here, .399, is the definition of a qualified person. So this is a qualified person. And this is what you're doing. So one who received training in and has demonstrated skills and knowledge in the construction and operation of electrical equipment and installations and hazards involved. So that's what we're doing in this class. Okay. So one of our main topics in this class, of course, is what? Safety. So we'll do lockout, tag out procedures on the line anytime we're working on it, and we'll look at when we need to lock out, when we don't need to lock out. But you went through a lot of that in the motor controls class. Employees who face risk of electrical shock that is not reduced to a safe level installation requirements must be trained. The occupations that are in table S-4 must be trained, other employees, if they face risk of shock. Now this is what I've done is I've copied that table S-4, and what I've done is highlighted all these occupations right here. Electrical and electronic engineers, electrical and electronic equipment assemblers, so that might be a job that you get. Electrical electronic technicians, which is definitely what you're getting trained for, and then electricians. So that means everything that we teach you in this school is covered by the OSHA 1910 subpart S. That says even though you work in this group, it says you don't need to be trained if you're not working on actually doing work on the equipment. Recognizing live parts, determining voltage of live parts and clearance distance, and we'll look at that too. So depending on what voltage you get into depends on how far you're supposed to stay away from those things when they're live. 333 covers locking and tagging, how to de-energize stuff, how to verify stuff is de-energized, how to the procedure for re-energizing stuff, right? Overhead power lines, being careful on those, illumination, and then several other tasks. Of course, we're going to be very interested in lockout and tags, so we have locks for the class. And of course, verifying that that you don't have any air pressure or fluid pressure, and you don't have any electrical pressure. So we don't put our life on a lock and a tag. So we're going to use our voltmeter to verify we have no voltage, even though we've got it locked and tagged, right? Okay. We're going to use a pressure gauge to indicate that there's no pressure in the system and we're going to bleed the pressure too. So what's the problem with pneumatics? Pneumatics are pressurized. So just because you turn off your compressor doesn't mean there's not pressure in the system. Okay, you understand? So what we got to get used to is bleeding that pressure off. Okay, we'll show you how to do that too. Are we okay? And make sure you have enough light to work on, right? 333 says live parts to which employees may be exposed shall be de-energized before the employer works on or near them, unless the employer can demonstrate that the de-energized introduces additional or increased hazards, or it is infeasible due to equipment design and operational limitations. Live parts that operate at less than 50 volts to ground need not be de-energized if there will be no increased exposure to electrical burns due to explosions or electrical arc. So what they've established is 50 volts. Anything above 50 volts, we're going to have to start considering. When I work on it, I'm going to have to do what? I'm going to have to de-energize it. 50 volts, it all depends on different things. That makes sense? So legally, our system, of course, this is a training system. Our systems here will operate on 24 volts DC. So that means we could operate on these, but we're not. So we're gonna treat this like it's a high lethal voltage just to get you used to doing this. Are you okay? 34E covers portable equipment, plug-in card, reclosing circuits, and inspection of equipment. 335 it covers PPE, or what we call personal protective equipment, but just about everybody calls it PPE. So if you ever hear that, that's what they're talking about. and what PPE we must use. Of course, in this class, the PPE we're going to use is we're going to wear safety glasses, right, with side shields. We're not going to wear cotton, right? We're going to wear long pants and no open toe shoes because we're not working with higher voltages. Then we get into 70E. 70E is the big thing that's out now. This is what there's companies that specialize in training on 70E, and a lot of your companies are adopting the 70E, and it covers safety in the workplace. These are the things it covers: a dangerous condition such that contacts or equipment failure can result in. So this is what 70E covers. It covers electrical shock, it covers arc flash, and it covers arc blast, and then of course thermal burns, getting close to hot things. Are you okay? Arc flash, electrical short circuits that occur when arc flashes from the exposed live conductor to either another conductor or to ground. So arc flashes or arc blasts are caused by electrical shorts. An arc blast is created by an arc flash. This is a pressure wave caused by the arc flash. That makes sense? And we'll show you some videos here pretty soon. So arc blast is concentrated energy. It's a high intensity flash. Temperatures can reach what? 35,000 degrees. I don't know why degrees isn't on there. And that's degrees Fahrenheit. That's in Fahrenheit, which is basically hotter than the sun. That didn't turn out too hot, did it? I don't know what came in at such a small font. Nope, that ain't gonna work. I'll have to find another one. In fact, I'll just probably spell it out since it's not working. This is going to be upset. All the problem we had trying to make this course with only one person showing up. So I'll send out email if you, especially the people that fought for the class to be made so they could graduate. So pressure waves the pressure waves coming off our arc blast can reach up to 200 pounds per square inch. That's a lot of pressure. Vaporized conductors in copper and exploded particles like buckshot. So what happens, 35,000 degrees, all the metal's going to melt. And then it's going to move out with the blast. And you got all this melted metal coming at you, right? Not good. Arc flash can cause severe burns, broken bones, vision damage, hearing loss, brain or internal injury, peripheral and lacerations, and of course what? Death. So when we looked at the slide about the number of deaths, this is what's caused most of electrical deaths, is this right here. Cause of arc flashes: improper training. People doing things they shouldn't do. And you'd be surprised what people do to get themselves killed. Improper work procedures. So normally if you follow the right work procedures, you have the proper training, then it's going to be very unlikely that you're going to get hurt. Drop tools, accidental contact with electrical system, insulation failures, inadequate short current ratings, so it means not using the right size fuse or breaker bows, voltage testing with improper test equipment. This gets a lot of guys in trouble right here. Trying to test voltage and not using the right category meter to test that voltage. Buildup of dust, corrosion, or insulating surfaces. This happens a lot where in industry things get dirty, right? And improper maintenance, sparks produced during racking or breaking, replacement of fuses or closing into faulty lines, inadvertentness or overconfidence. This helps a lot. This hurts a lot of people too. Racking a breaker. These are, when you think about breakers, you think about the breakers in your house. When we get into industry, we're talking about sure enough breakers. So we'll see if this link works. So they're racking a breaker right here. So this is a breaker box, and they've got the breaker out. Now, one of the things you got to notice here is that you see this hole in the door right here. Now, what do you think that hole's in the door for? So they can rack this breaker or insert this breaker into the panel box. Now, this breaker is so big that they put it on rails and they literally just crank it in there and goes in, and then the connection is made back in the back. In fact, let's see if we can look at some high voltage breakers. They got some explosions. No, those are showing. These are actually showing. These are actually breakers for transmission lines. One of the things that we did. So this is a high voltage breaker right in here. If you can see this. There's another better picture. So this is a high voltage breaker. So notice it's on wheels, bearings, and then these are the actual contacts that go in and insert into the panel. Here's the actual little breaker right here. So they get these breakers out and they service them or maintain them, and then when they rack the breaker, that means inserting this big old breaker into the power panel. Now a lot of them, they got this little crank on the bottom that literally cranks the breaker in. And most of them now, you actually do it with the power panel closed. But when you look at this video right here, here's the hole in the door, so this guy could have this thing closed. But he's in here, and basically you use I forgot what they call it, a wrench type thing, handle. Yeah, you can see him in here turning the thing. Now this guy right here does put his face shield down. This guy right here don't even look like he has his face shield down. So there's two guys working on it. I don't see full screen. I don't think there's any sound. You see him racking the breaker now? So he's turning the thing and racking it in there with the door open. Now this is one of the most dangerous times of putting these big old breakers in, is when you're putting them in. They call that racking, or unracking means to take them out. This guy just saved his life. There's different people that talk about this. Some of them say the guy survived. Some of them say he didn't. I don't know how he survived because he's right there. And boom. So that was an arc blast. So you think he made it? I don't know. I don't know. So that's called racking a breaker. This is just a standard breaker box demonstration. And I'm sorry, I can't. This is a YouTube video, but it won't. Here we go. It wasn't on the other one. And this is an arc flash off a breaker panel. Now that's not a person there. That's actually a dummy. So they look at knocked his gloves off. So they deliberately created an arc blast on a panel box. So that was a breaker box demonstration. It was play. You didn't hear it, but it was playing in my headset. So 70, and after 70, one who has skill and knowledge related to the construction and operation of electrical equipment installation and has received safety training to recognize and avoid the hazards involved. So that's basically what the 1910 says. Qualified persons understand specific electrical hazards, knowledge of the construction and operation of equipment. So this is one thing that we're going to make sure we understand is that before you can work on equipment, you got to have what? You got to have some idea how it's constructed and how it operates, right? In fact, that's my basic rule of troubleshooting. Number one is to do what? Understand how the equipment operates. Identify and understand the relationship between electrical hazards and positive injuries. Distinguish where the exposed parts are. Be able to determine the voltage of live parts. So what that means is before you get into a piece of equipment, you need to understand or know what voltages are available inside that equipment, right? Of course, we know what's available here. We got 24 volts in the system, and we got 120 volts at the power supplies. So we'll go over there and look at the power supplies in a minute. Able to determine voltage of live parts, understand and complies with arc flash and shock hazard boundaries. Proper use of precautionary techniques, the personal protective equipment and arc flash shock protection, insulated gloves, which we don't require in this class. We did in the motor controls class, but we don't in this class. Decision-making process, demonstrate how to select and use a voltmeter. So one of the things we're going to do in this class is we're going to do the NC3 meter certification for y'all. So that's one of the things we have planned for the class. If they let it make. Right now, I'm not sure. The class was going to make, but only one person out of 7 people show up. That's not good. Decision-making process used to determine degrees and extent of hazards. The 70E, section 130.1. Are you okay? You need a break? Deals with energized electrical conductors and circuit parts to which an employee might be exposed shall be put into an electrically safe work condition before an employee works with the limited approach boundary of these conductors and parts. Unless the employer can demonstrate that the introduces additional hazards or is infeasible. Interruption of support light system, deactivation of emergency alarm system, shutdown of hazardous location and ventilation systems, circuits and conductors that operate at less than 50 volts. Other work may be performed within the limited approach boundary of exposed energized electrical conductors if you're doing what? Testing, if you're doing what? Troubleshooting, or you're measuring voltage. So that you cannot check voltage when the power's off, right? Or you can't check the operation if the power's off. So testing and troubleshooting, odds are we're going to work on the energized equipment, which means we're going to have to be extra safety. But anytime we do a repair, then we're going to lock and tag. Okay, so anytime we do maintenance, we're going to lock and tag. When we troubleshoot, we're going to troubleshoot with power on. Everybody, you okay? De-energized lockout policy, don't wear conductive apparel, work area with good illumination, and we got great illumination in here in this classroom. Never reach into blind spots. Don't allow conductive liquids near electrical work. Buddy system, which means if you work over 1,000 volts, you're supposed to work with at least 2 people, right? At US Steel, it was 500 volts. So if we ever worked on over 500 volts, we had to work with 2 people. Do not defeat electrical interlocks and use non-conductive ladders. The first electrical instructor that we had here bought ladders for the commercial wiring class and residential wiring, and he bought aluminum ladders. When Mr. Sanders came in, he said, no way. So now we have fiberglass ladders. So this is an example of an arc flash label. This tells you the flash arc boundary. This tells you the actual flash hazard. Flash hazards, by the way, are rated in calories per centimeter squared. And there's a pretty good math formula that you have to do. Most people don't do it on themselves. They'll call in a company that specializes in arc flash. So what happens is that there's several things that determines this right here. And this depends on the voltage, it depends on the current, the opposition, the resistance. So the further you're away from the power source and the more transformers that you go to, then this right here will drop down. So in our house, we work on we have 120 volts, which is considered to be lethal, but it's got a very low calorie per centimeter squared because you come through a transformer and different things in a power box and a panel box to get to where we're working on that. So category 0, this is what category we're going to be dealing with, which means you need to have untreated cotton clothes. Okay? Covered gloves, we're not going to use that because we're only dealing 24 volts. But this is 156 inches, but this is a category 2. So the further you go up into the categories, then the more PPE you got to have, right? And this shows you the risk categories, calories per centimeter square. And like I said, I've seen the equation somewhere, but the actual risk hazard is going to be 0 through 4. And anything over 4 is labeled as what? Dangerous. So we're down in this category here. This is the category that we're in motor controls because of where we're at. Okay? We have different approach boundaries. We have a flash protection boundary, a limited approach, a limited space, a restricted approach, a restricted space, any point on the exposed energized electrical circuit, prohibited space, which nobody gets in here, right? And then prohibited approach boundary. They calculate all these. Qualified workers responsible for ensuring physical barriers are replaced and all approach boundaries are enforced during work. So if you go to work on a company that's got a pretty high rating, arc flash rating, then what you're going to see is you're going to see boundaries on the floor. And they have to put those on the floor, which says, okay, if you get in within this boundary, you can walk this safe distance. You're outside the arc flash, arc blast. Then you get into this distance, and you're going to have to start putting on personal protective equipment. And the closer you get, the more PPE you got to understand, and the more training you're going to have to understand. And this just shows glove labeling, which we really don't need to get into. We're not going to wear gloves, but they specify what glove rating you have to have. So if you're in a category Z, you're supposed to wear gloves that are this color rating right here, which would be brown, all the way up to category 4, which would be rated orange. Then they get into voltage rated gloves. First line of defense, choose the right size. Leather gloves protected over rubber gloves. And it says gloves must be tested what? Yeah, but you're supposed to have them tested too. So you're supposed to have them tested every what? 6 months, yeah. If tested but not issued for service, gloves may be unless tested within 12 months. So if you buy gloves and you put them on a shelf, you're still supposed to have them tested every what? Every 12 months. If you wear them, you're supposed to have what? Every 6 months. You okay? You okay? Of course, arc rated, and we're not going to get into all this. So notice this is 0. So this is basically what we're supposed to wear in this class right here. We're supposed to wear what? Long sleeve shirts, long pants, safety glasses, hearing protection, leather gloves, and leather work boots. So that's what we should have wore in motor control. Okay. But we don't. We're only 24 volts here, so we're. But when you get into 1.2 to 4 calories, then you start getting into what? Yeah, arc rated face shields, hearing protection, VR rated gloves, voltage rated gloves, leather gloves. So you're supposed to have plastic glove, rubber gloves under your leather gloves. Can you see that right there? Yeah. And leather work boots. Then you get into this one. Then what changed? Yeah. So what you got to do now is So here you have to have here you wear a cotton long sleeve shirt. Here you wear calorie rated long sleeve pants and coveralls. Okay. Here you do what? It looks the same, but now your short sleeves have to be rated 8+. That makes sense? And then we get into 825. This is when you start putting on your bunny suit, right? 25+ rated hoods over long sleeve shirts and long sleeve. So here, safety glasses, hearing protection. Okay, then you get into this guy right here. Then you got a flash guard hood over a long fire resistance long sleeve shirts, long pants, safety glasses, hearing protection, voltage rated gloves, leather gloves. So you got rubber gloves rated for the voltage, then you got leather gloves over that. So what PPE you get into depends on what calorie you're in. Yeah. So here we're below 50 volts. So actually this comes into play over 50 volts. So we're requiring you to wear what? Long pants and no open toe shoes.